So yeah, our project is all about understanding how to improve the properties of post-consumer high-density polyethylene. So we've heard lots of different talks covering kind of novel or new materials. Here we're looking at probably, well, the second most widely used commodity plastic in packaging. Our team was really diverse, cutting across both institutions, but also a whole range of disciplines. So we've got data science, supply chain, management, material science, and chemistry. Okay, press the right way. Yeah, it's that way. So just to really set the scene, and again, I think I'm probably preaching to an audience that knows quite a bit about this. High-density polyethylene is about 50% of our bottle packaging in the UK, about 250,000 tonnes annually. In terms of its life cycle, of course, once we've used the bottle, we hopefully put it into the appropriate recycling option. It will then be sorted and baled at your materials recovery facility, and then those bales will then be typically sold on to a reprocessor who will flake the material and make this pellet. So this pellet is our post-consumer recyclate, PCR. About 40% of the material that's actually used in packaging makes it to this stage. So that's already a lot being lost into landfill and incineration. But one of the fundamental problems that even though we get 40% of the material here is that actually this is a highly variable product. And this is probably the worst possible example you could find. We can see the variability just in the color of the pellets. Why is that? Well, first of all, we have mixed grades of HDPE are actually used here. So there's different grades of milk used for milk bottles, bleach bottles, shampoo bottles, all have subtly different grades. That then, of course, feeds in. We also get contamination, which I'll talk about more briefly later on, and also we get degradation. So a lot of material here doesn't end up going back into packaging because the quality just isn't sufficient, so it goes to lower value applications. Our project wants to address this knowledge gap that relates the properties of this plastic to its performance and then be able to decide whether it can go back into bottles and also how to improve it. So ultimately we want to be here so we can get more of our plastic back into bottles and hopefully also incentivize more collection and recycling, partly through driving more value to our PCR side. Okay, so this is an image everyone's, well, a lot of people in this room have seen. I'm sure I stole it from Nick actually originally. Is obviously, but we've gone from this transition of how plastics really enabled us to live life very efficiently in a way, not from a materials perspective, but just from a convenience. And we want to transition over to our circular aspect in terms of the circular economy. So the bit we're really thinking about is after the collection, baling, sorting, where these bales go into recyclers, what's happening here, what are the factors that controls the properties of our recycled pellet. Of course, there's many driving factors going on at the minute. So we've got the plastic packaging tax, which has definitely influenced some of the behaviors. We've got the plastic pack targets, which obviously actually framed this call EPR underway, and also deposit return schemes often on the cards. So these factors are all feeding in, but still we have to know how to produce high quality recyclate. So what's one of the big problems? What happens to HDPE upon mechanical recycling? So here's an example of a broken bale. This is provided by a materials recovery facility. So we can see, first of all, I'll go back. First of all, we definitely have a whole range of different plastics in this mixed plastic bale. We have things like, here's our milk bottle. We have a lot of plastic wrap. We have paper somewhere. We have a whole range of different materials. Polypropylene's also mixed in there. We'll have some PET. So that's one problem that's often obviously heavily linked to our sorting technologies. The other problem, which I think is really key in the HDPE space, is our bottles are made out of the HDPE, but our caps are typically made out of polypropylene. And so this ends up becoming something that often contaminates our HDPE feedstock. Also, one of the other things, I'm not going to have time to talk about it today, but obviously every time we recycle plastic, we introduce an additional degradation step. So this is something we studied at Manchester and Mike was leading on, who will be talking in a couple of talks' time. He won't be talking about that, but that was also something we wanted to study. What happens as we do repeated extrusions? How can we try and offset that degradation? Okay, so This wasn't our first project in this space. I'm not going to talk about it, but we started on a Plastics Research and Innovation Fund, which was again focused on high-density polyethylene. Here we're looking at the problem of stress cracking, environmental stress cracking, which is a big problem in HDPE. But of course, what I want to talk about today is our SSPP project. And really the key thing that makes up this project is a coupling of chemistry and material science with data science, because as I'm going to show in a minute, we generate a lot of data and we can't just process that in a traditional material science chemistry way. I'll explain in a minute. But we also look at some supply chain to understand what's happening. Again, I won't have time to talk about that today, but that was another element. And this was underpinned with really close and informative collaboration. So IPL Bright Green, Jonathan's here today. He'll be on the panel tomorrow. And also, so IPL Bright Green recycle HDPE and polypropylene. They were able to share their knowledge and insights into the project. And of course, Unilever are a huge producer of plastic packaging. So we kind of had both sides of the supply chain informing into our project. So what does our project actually look like? Well, we wanted to understand our material. So we got a wide range of different commercial PCR bottle grade, because we were looking at non-food applications. I should have stated that before, non-food applications in bottles. So we worked with Unilever, Bright Green Plastics, other PCR suppliers in the market to obtain a whole range of different materials. We then used 10 or more different characterization techniques. Now, these are all ones that have been shown in the literature or have got a good track record in industry for characterizing the materials. And of course, when you characterize a sample, you generate data. Now, here's an example of a differential scanning calorimetry, heat and melt scan. And so each sample you run obviously is going to give you different aspects. So we're looking at features. So features were things we could use to differentiate the samples. And here's an example where we've got, this is actually the melting transition of polyethylene, and this is the melting transition of polypropylene. So this sample's got some polypropylene in. So we can look at a few different data points here. So the melting point, the actual temperature, the energy associated with this, the range of temperatures occurs over, each of those is a feature, and each of those has really potentially valuable data buried within it. So by using this combination, we generated 25 unique features per sample. I'll explain in a bit more detail. And that generated us 3,500 nearly features for each sample. This was a lot of work done by a team, including Andy, Emily, and Pei Yao. And we also looked at replicates, so we can understand the variability within a batch, but also the noise within our experimental technique. So we wanted to also, of course, have techniques that spanned across the different properties of the material, from the chemical scale all the way up to the bottle property. Obviously, we can measure aspects here, and it will inform the properties over in its actual bottle aspect. So we looked at chemical, polymer architecture, melt properties, crystallinity processing. We looked at tensile testing, so a surrogate that hopefully informs bottle properties, just to understand our material. And this is the largest study of real-world post-consumer materials to date. So here's kind of a figure that tries to pull the concept of a big chunk of our project together. So here's our sample set. And each one of these represents a type of test. So we've only got 6 different tests out of our 10 shown here. So we got infrared spectroscopy, differential scanning calorimetry, thermogravimetric analysis, rheology, mechanical testing, and color testing. And each, as I was saying, each type of testing will generate features. So this middle section, this heat map, shows kind of along the bottom, we have our different samples, our different PCRs and some virgin reference samples. And along this axis is essentially the different features. So I'll talk about it in a bit more detail on the next slide. But these are the features taken from our tests. And then what we do is there's a lot of complexity there. So how do we then make that more accessible? And this is where the data science comes in. We use principal component analysis, which is a technique that looks at the ways you can look at the directionality in the data. So if you imagine you've got a multi-dimensional space, you're finding a line that cuts through that multi-dimensional space and allows you to separate those different data points. And what it does is it takes all this data and essentially gives us 2 axes which contain these different features. And so we do this for every technique, and then we do another round of principal component analysis to generate our final data. So I'll talk through this with an example of 2 tests now, because I know it's probably a little bit complex. So I'm going to talk about it about FTIR, and then I'm going to talk about it with thermogravimetric analysis. So FTIR is a really standard, really convenient way of measuring samples. You essentially put your sample on the spectrometer, and you can make a measurement in 1 minute. So what does that generate? Well, it generates 6 characteristic peaks, which are common for all polyethylene, shown here. Not great, those peaks, in terms of differentiating your sample. So you have to look beyond that. And the literature, again, has got lots of really useful identification of peaks. So here's an example. If we zoom in just over here, we've got this kind of graph which looks at these wave numbers. And we can see that there's a peak that's different for some samples compared to others. So this is actually a signal for polypropylene. That's really great, but if you've measured thousands of unique measurements, you're not going to individually go through and find the peaks. So what Phil did down here, who's our data science postdoc, he looked at saying if he could use the second and third derivative of this spectrum to essentially allow him to have high sensitivity for detecting both the peaks and also potentially shoulders that often occur on some of the peaks, and do that in an automated way. And so where we got to is this heat map down here. So this heat map, unfortunately you can't see the bottom axis. The bottom axis is the wave number. So it's essentially along our x-axis here, and here's all our different samples. So where we have color, an orange color, tells us we have a large signal there, and where we have the kind of purpley color, we have nothing. So what we can then see is what wave numbers help us differentiate samples. So there's certain wave numbers that are very strong in specific samples over others, and we use our virgin samples as obviously a comparison of kind of a high quality material that we'd like to replicate. And then by using the literature, it's possible to then identify what some of these things are. So polypropylene being one of our key contaminants or key kind of components that's often there. We also see that people have often added in this ergophos, which is an antioxidant. We've got examples of PET contamination in some of the different samples. Calcium carbonate's potentially been added a filler. We've even got some evidence of polyamide, which could be mixed in from kind of a potentially slight contaminated stream. Maybe some flexibles have been incorporated there. So again, it's a really effective way to quickly crunch the data. Okay. And then if we look at thermogravimetric analysis, so here essentially we just heat a sample up and look at mass loss as it degrades. This is the first derivative of that mass loss. So as we heat it up, we're beginning to see mass loss occur here. Phil, again, traditionally in material science, we just look at a couple of things. We look at the onset temperature, and we'll typically look at how much mass is left after we've heated it, so the residue. But again, Phil kind of had a new view to it. He wasn't aware of normally how people would focus on it. So he's like, what features can differentiate these samples? So he identified a few different regions where we look at the change in the first derivative here, in the different bands shown, and then related those to the samples. So here again, so these are lower temperatures, and then we're increasing temperature here. So these actually tell us a lot about the volatiles. So we can see when the volatiles are being lost from the sample. This feature 3, we actually think tells us a lot about degradation of some contaminants within the material. And again, now we can heat map those, and we can again see that there's some samples that show very big differences compared to one another. So our virgin materials actually show more heat loss, more loss in some of the lower masses for some of the volatile components, whereas other samples show very little residue in the case of the virgin samples. And here's our principal component analysis. So each axis essentially contains combinations of these features here. And again, we can see that our virgin samples tend to cluster, and we notice some samples are closer than those, whereas other samples will be much more different, so they'll have different degradation behavior compared to virgin. So how do you make all that meaningful? Really, it's great being able to test the samples, but we have to have some insight. We have to be able to think about how can we choose better quality recyclates. So by combining each of those 6 principal component analyses, I showed you 2, we chunk them together into this. And now here we can see in this bottom corner are 3 virgin samples. And essentially now we can see which samples are most similar to virgin. So we can see, for example, PCR 15 down here is really similar, whereas if we were looking at maybe PCR 21 or 23, that's a long way away. We of course know what are the features that make this up. So polypropylene is a key differentiator, unsurprisingly. This component here is much more complex and contains information about rheology, the volatiles present within the sample. But again, it allows us to quite quickly select samples. Okay, that's all well and good, but of course it's not going to be possible for someone in industry to get a sample and put it through 10 different techniques or 6 different methods. We can't do this, it's not practical. Some of these techniques aren't going to be available in a recycling plant. So we were looking at what tests can we select out of that? So we were trying to look at what triplets of tests are most informative. And the way we did that is essentially, here's our example I was shown before. But of course, we could take the data and just say, what does it look like if we've got 3 types of characterization technique? And then we can look at how much the data points, I'm oversimplifying it here, but we can look at how much the data points move relative to an average of the virgin samples. So we can kind of see, is the same ability to separate the samples retained if we just use 3 tests? And so this is what's shown. So essentially, in this case, a bright yellow color tells us it's bad. A high number tells us there's a lot more, our data point has moved a lot relative to where it is with all tests. So these samples, these combinations of testing methods provide little insight, limited insight, whereas actually if we take thermogravimetric analysis, FTIR and mechanical tests, we actually only lose about 20% of our separation of data. So we can really simplify and just use 3 quick tests to test the material. So that's what we've shown that works. And these are the ones that lead to the lowest loss of differentiation. Of course, that's really great because TGA, FTIR, and mechanical tests are all very common tests that can be done in industry. Another thing we've looked at, and people have always, if you speak to anyone in industry and they tell you polypropylene is a big problem in HDPE. I mean, this isn't groundbreaking, but this is really conclusively showing the effect of polypropylene in kind of reducing the properties of HDPE. So here's normalized strain at break, so essentially how long you extend the sample, what length it's extended over before it breaks. And our bottom axis is essentially, you can't see it, but it's the polypropylene content. So the minute we begin, so our virgin samples are here, they have no polypropylene content in. The minute you have any real polypropylene in there, we'll see a massive drop off of the elongation to break. That's because it's an immiscible polymer, and so that phase separation leads to much more brittle failure in the material. We also showed that you can get a really good indication of the amount of polypropylene in the sample just by an FTIR measurement. So DSC is the standard, but FTIR, again, we showed actually we can have almost the same degree of sensitivity as DSC. Okay, whoops. So quick summary on that bit. So I think we've shown that PCR can be effectively identified and classified. We've looked at 23 samples in total, so that's 20 PCR samples. We've shown we can differentiate the samples. We've looked a little bit at the relationship. I've only been able to talk about the polypropylene content there. And one of the key things we're doing now in the last few months of the project is trying to identify the other properties and link them to bottle performance. Excuse me. So the other things we've been doing in the project, which I haven't really had time to talk about, is our supply chain work. We've been looking at the economic, environmental analysis and practice in policy changes associated with supply chain, recycling supply chain. So looking at kind of what is the Plastic Pact been doing in terms of what's happened in the supply chain. 5 minutes, thank you. Another thing we're doing, so this is funded by Impact Acceleration Award, is, again, it's all well and good. We've got this data set that tells us and helps us predict the properties of the material, but that needs to be usable by someone who's not Phil. like our data science expert. So what he's been doing is he's essentially been working on generating a software tool that can just plug in. We're looking for something that's in a web browser that can then essentially allow us to say, you input some data on the material and it will then give an output in terms of, we think the likelihood is going to be, well, it will give an ability to measure the polypropylene content off FTIR data, and also where does it sit in terms of our kind of similarity to virgin. We've got some other work which we'll be looking to publish in the coming months, where we looked at processing, as I talked about, multiple extrusions. What is the effect of the degradation that can occur there, and can we improve the properties of PCR? And finally, and really critically, we work with Unilever to do bottle tests. So we've selected resins from essentially around our 3 different segments. So we've selected resins that are similar to virgin over here, samples that are in this area where we know they've got lots of polypropylene, and in this region here where we've got a wide range of different subtle differences in the material. And we've got the data to kind of predict, well, we've got the data on the bottles and their performance, and we then want to be able to show that and publish on this to show that certain materials, depending where they sit on here, are more likely to succeed in bottles or not. The challenge here is really bottle failure and bottle performance is a bit more black and white. It either fails drop test or it fails pressure test than many other characterization techniques. So that's something we're going to get out in the next couple of months. I have an acknowledgement slide, so I'll just freestyle and obviously say that, yeah, these kind of things are really a key team exercise. So it's been, just to kind of reiterate what everyone else has said though, it's been a real privilege, I think, to work with a whole range of different disciplines. I've learned so much, and I think also the industrial partners' input to the project's been really invaluable. And I think, again, something that's been really enjoyable is the involvement in the SSPP and actually these kind of events. So yeah, I obviously wanted to put the people's faces up who've done something. Oh, it might get there. See that? I think this animation is what's breaking it. Yeah, so there's all the different people who've contributed to the project, and yeah, thank you for your attention.